So in this lecture, we will discuss about some numericals related to the AC circuits. This lecture will cover the numericals related to series AC circuits, parallel AC circuits, on power and power factor, and on resonance in AC circuit. So to start with, the first numerical is in which the statement is mentioned that there is a pure inductive coil which has some current which is 10 ampere that is flowing through that coil, and the voltage source to which this coil is connected is 230 volt and 50 hertz. So that means we have an AC source which is having some voltage which is equal to 230 volt, and an inductor of some inductance L which is not known to us is connected to this voltage source. Right now the RMS value is V, which is equal to 230 volt, which is given, and the current is 10 ampere, and this is a 50 hertz AC source. All right, now we have to find out the inductive inductance of the coil, power absorbed by the inductor, and then we have to write the equation of voltage and current in this case. So the first is we will find out the inductive reactance. Now inductive reactance is given by XL, and XL is basically 2 pi FL, but here L is not known, it is not given. So what we will do is we will use the simple concept V is equal to IXL, or XL is equal to V by I. So by using this equation, we can find out the value of the inductive reactance, which is 23 ohm, because the reactance is measured in ohms. Now this is the answer for this one, 23 ohms. Now the second part is that we have to find out the inductance of the coil. Now inductance is L. So by using this, XL is equal to 2 pi FL, and from here we can have L is equal to XL by 2 pi F. So this is 23 divided by 2 into pi into F. So it is equal to 23 by, this F is nothing but 150. This is 50 here. So it is 100 pi. So this is equal to 0.073 Henry. So this is the value of inductance in this particular case. Similarly, we can find out the third part, which is power absorbed. Now, as we all know that an inductor does not absorb the power, only stores the power. So hence, power absorbed by an inductor is 0, right? Then we come to the fourth point, which is we have to find out the equation for the voltage and current in this case. Now we know that the value, the equation for the voltage is given by V is equal to Vm sine theta, and I is equal to Im sine theta minus 90 degree. Now why it is 90 degree? Because we know that the current lags the voltage VL, and VL is the voltage here across this inductor, by 90 degree. Or we can also say that VL leads I by 90 degree. Both the statements are true. I lags VL by 90 degree. These both statements are true. So that means we need to know the value of Vm. So Vm is nothing but it is equal to V into root 2. So it is 230 into root 2. Similarly, Im is nothing, because we know that V RMS is equal to Vm by root 2 for a sine wave, right? Uh, this is for sine wave. Similarly, Im is equal to I into root 2. So this would be equal to 10 root 2. So this is 14.14 ampere. This is the peak value of the current. And similarly, we can calculate this 230 into under root 2 will be equal to, it is equal to almost 325.27 volt. So now the equation for voltage is equal to 325.27 sine theta, and I is equal to, or we can also write it as 325.27 sine omega t. And similarly, I is equal to Im. Im is 14.14 ampere sine theta minus 90 degree. Or we can also write I is equal to I. This is 14.14 amp, not amp. Amp. We don't have to write ampere here. Sorry. Uh, So current is equal to, because it is equal to Im sine theta minus 90 degree. So it is 14.414 sine theta minus 90 degree. Or we can also write I is equal to 14.14 sine uh, omega t minus 90 degree. So because theta is equal to omega t. So this is what we have used here in this particular question. So the four things we're supposed to calculate. We have calculated the inductive reactance, the inductance of the coil, and power absorbed is zero because an inductor does not absorb any power. It does not dissipate any power. And finally, we have obtained the equation for voltage and current. Now here in this two, there are two questions on this particular slide. In the example number 2, we have to calculate the, or we have to write the mathematical expression for the voltage across the inductor, which is connected to a voltage source, which is delivering this much current, right? So let us draw the circuit diagram first of all. So we have an inductor which is connected to a voltage source, AC voltage source. So this voltage source is delivering some current I, and the RMS value of voltage across this voltage source is V, and its value is given by V is equal to Vm sine, let us say, theta, and L is the inductance of this particular inductor. Now we are supposed to write the equation of the voltage for this particular case. Now the given parameters are, given is, right? So I is given, I is equal to 0.1 sine 440t minus 25 degrees, right? Now, from here, if we compare this with uh, the standard equation, so we will get this is equal to Im. So here Im is equal to 0.1 ampere, and L is given as 80 millihenry. So 80 millihenry is equal to 80 into 10 raised to the power 3 Henry. Now we have to write the equation for the voltage. So the equation of the voltage, or the expression of the voltage across inductor is, because this is the only component which is connected to this voltage source, and the voltage across this is, let us say, VL. So VL is equal to V, where VL is the RMS, both are the RMS values. RMS values, right? Now, the voltage expression is given by V is equal to Vm sine. So it is omega t, and then minus 25 degree plus 90 degree. Now, because we know that the voltage leads I by 90 degree in inductor. So we have taken this one. So from here we have V is equal to Vm sine omega t plus 65 degree. So that means we have to calculate Vm. So Vm can be calculated by using the equation Im into XL, right? So XL can be obtained by using the formula 2 pi FL, so which is equal to 2 into pi into 50. Now, 50 can be obtained by using this, no, this F, sorry, F can be obtained because we know that omega t is equal to 440 t. So omega is equal to your 2 pi ft is equal to 440 t. So this is cancelled out. So F is equal to 440 by 2 pi. So this is almost, so XL is equal to, so 2 pi F can be taken as 440 here. So this is 440 into, and L is 80 millihenry, so it is 80 into 10 raised to the power minus 3, and this would be equal to uh, 35.2 ohm. Now we can find out, we can put this value here in this one, so we will get the peak value of the voltage. So Vm is equal to 0.1 into 35.2, so it is 3.52 volt, and hence the equation for the voltage will be equal to we can substitute the value Vm in the equation as given above. No. So V is equal to Vm sine omega t plus 65 degree. So it is equal to 3.52 sine omega t plus 65 degree. So this is the answer for this particular question. So this is how you can find out the answers for the given such type of questions. Now similarly in the second question, which is related to not to the inductive circuit or inductor, it is related to the capacitor, which is connected to our source, which is having 230 volt as RMS value and 50 hertz as its frequency. So that means we have the solution is that we have a capacitor which is connected to a voltage source, AC voltage source. Now, the capacitor is connected here, which is equal to 318 microfarad, and the current here is I, and the voltage across this is V. So this is a 50 hertz source, 230 volt and 50 hertz source. So we have to find out the capacitive reactance. We have to find out the RMS value of the current. Means this I, we have to find out equation for the voltage and the current we have to obtain. The first is XC, which is capacitive reactance. So to determine XC, what we will do is we will use the concept formula 2 pi, not 2 pi, sorry, it is 1 by 2 pi FC. So let's rewrite this equation. So XC is equal to 1 by 2 pi FC. So it is equal to 1 by 2 pi, F is 50 hertz, and C is 318 into 10 raised to the power minus 6 farad. So the value of XC is equal to, so it is almost 10 ohm. So this is the capacitive reactance, which is the first part. Second part is we have to find out the RMS value of current. So the RMS value or the RMS current is given by I. So I is equal to V by XC. So it is 230 volt divided by 10. So it is 23 ampere. And third, we have to write the current and voltage equation. So in case of a capacitor, because we know that the current I leads the voltage VC, because the voltage across this would be VC. So by 90 degree, current leads the voltage by 90 degree in case of a capacitor. So we can write it like this. V is equal to Vm sine omega t, and I is equal to Im sine omega t plus 90 degree, right? So we have to find out Vm. So Vm can be obtained by using the equation V into under root 2. So V is 230 into root 2, right? So similarly, we have the current, which we can use the peak value of current Im, this is volt. Im can be I root 2, so it is 23 root 2 ampere, right? So we have the values. So Vm is equal to 325.27 volt, and Im will be equal to 32.53 ampere. Now we can write the equations. V is equal to 325.27 sine omega t, and I is equal to 32.53 sine omega t plus 90 degree. So this is how we can find out the answers. So we have obtained all the three things which are being asked in this particular question. Xc, the capacitive reactance, the first part, and then the current RMS value of current, the second part, and then we have also written the equation of the voltage and current in this case, the third part. Now this is the example number 4 of today's lecture. In this example, there is one coil given which has some resistance, and there is some inductance of the coil, and these two are connected in series to one another across a 230 volt source and 50 hertz. Means the frequency of this voltage source is 50 hertz. We have to calculate the current in the circuit, the series circuit. We have to calculate the phase angle, power factor, and the power consumed, and the voltage drop across the resistor and capacitor. That means, not capacitor, inductor, sorry. We have to find out VR and VL. So let us see how will we calculate this. This is a typographic error, so it is ohms. Now, the circuit diagram of this question would be like this. We have a voltage source, which is AC in nature. We have a resistance. We have an inductor of the coil. So R is 7 ohm. L is 31.8 millihenry. Capital V is the RMS value of this voltage. Capital I is the RMS current. So given is, so V is given, which is 230 volt. Frequency of the input signal is given, which is 50 hertz. The value of R is 7 ohm, and the value of L is 31.8 millihenry. Now we have to find out, the first thing that we have to find out is the circuit current. So how will we find out circuit current? So circuit current is this one, I. This is the only current which is flowing in this particular circuit. The circuit current is I. So now, how can we find out I here? So here we can use, because this is a series circuit, so we have to find out the impedance. So we know that I is equal to V by Z. So Z is the impedance, and it is equal to R square plus XL square. Now, to find out the value of I, we need to find out the value of Z, because V is given. So Z is equal to under root, R is 7 ohm, so 7 square plus XL. So XL we can find out, because XL is nothing but 2 into pi into F into L. So L is 31.8 into 10 raised to the power minus 3 Henry. So this is how, and the square of this one. So frequency. Now we can find out the value of I. The circuit current I can be calculated as V by Z. So it is 230 volt divided by 12.2 ohms. So it is almost 18.85 ampere. So now the phase angle phi XL is equal to 10 ohm. So we can put it here, 10 divided by 7. So phi will be equal to 55 degrees. So that means in this case, the current lags the voltage. I lags V by 55 degree. So because this is an inductive circuit, so we will write lag here, so that we can distinguish, or we can understand from the value of phi that which type of circuit could it be. Then we have the next part, wherein we have to find out the power factor. So the third thing is the power factor. So power factor is nothing but we can write R by Z. So it is R is 7 and Z is R 12.2. So the value of power factor is equal to It is 0.57. So this is cos phi, and then we have to find out the power consumed. So the power consumed can be obtained by using, so power consumed is the power absorbed by the circuit, which is Vi cos phi. So it is equal to, P is equal to 230 into, no, I is 18.85, and then we have 0.57. So it is almost 2484.24 watts. Then the last we have to calculate is voltage drop across resistor. So voltage drop across resistance is given by VR, which is I into R. So it is 18.85 into R is 7 ohm. So it is equal to, so it is equal to 131.95 volt, and VL will be equal to IXL. So I is equal to 18.85 into XL is 10 ohm. So it is 188.5 ampere. So in this, we have understood how to calculate the various parameters in a circuit in which a resistance and capacitor are connected to one another in series. So now let us take the next numerical, which is example number 5. In this, an inductor coil is connected to a supply of 250 volt at 50 hertz and takes a current of 5 ampere. The coil dissipates 750 watt. Now, this is an inductor coil, but it also dissipates the power. So that indicates that this is an RL circuit basically, which is connected to a 250 volt source. So this 250 volt and 50 hertz. So this 250 volt is basically the RMS value, and the current is 5 ampere. So this is also RMS value of the supply. Now why I'm saying that it is RL circuit, because it is dissipating the power, and we all know that inductor does not dissipate any power. So if the circuit is dissipating the power, so that means it has some resistance connected with it. So now we have to find out the power factor. So power factor is nothing but cosine of phi. So this is cosine of phi. This is what we have to find out. R we have to find out, and L we have to find out. So let us see how will we calculate these parameters. Now, as we know that cos phi is the ratio of the power dissipated to the source power. So P here is 750 watt and VI is 250 into 10. So this is 0.3. So this is 0.3, and because your circuit is an inductive circuit, so it is a lagging power factor, right? So then we have the resistance. So we also know that cos phi is also given by R upon Z, right? So from here we can find out R, which is Z cos phi. But for that we need Z, and Z is basically given by the Ohm's law. By applying Ohm's law here, we know that Z is equal to V by I. So V is 250 volt and I is 5 ampere. Sorry, there's a mistake. This is 5, right? So this would be 0.6. So we have this 50 ohm. Now by substituting this value here in this equation, we will get R is equal to 50 into 0.6. So this is equal to 30 ohm. So the value of R is 30 ohm. So this is another answer, 0.6 lag. Now I am saying it as lagging because it is an inductive circuit. So I'll write it here. Because inductive circuit. right? So that you can remember this one. Then we have third part. So third part is in which we have to find out the inductance of the coil. So inductance can be obtained. We know that the inductive reactance is equal to 2 pi FL. So from here we can find out L is equal to XL by 2 pi F. But XL, as we know that the impedance is equal to under root R square plus XL square. So XL is under root Z square minus R square divided by 2 pi F. So by substituting the values here, we get 50 square 2500 minus R is 900 divided by 2 into pi into 50. So your inductance is equal to, on calculating we have got 0.127 Henry. So this is the answer for this particular question. Now let us come to example number 6. So example number 6 is almost similar to what the example number 5 is. So in this we have an inductance of this much is connected in series with a pure resistance of 75 ohm basically. So this is 75 ohm. The circuit is supplied from 50 hertz source and the voltage across the 75 ohm resistance is found to be 150 volt. Now we have to calculate the supply voltage and the phase angle. So the solution for this is, now the given parameter R inductance is given, which is 318 millihenry, or it is equal to 318 into 10 raised to the power minus 3 Henry. R is given, which is 75 ohm, and the diagram is shown here. Now this VR is equal to 150 volt. So this is given. VL is not given and V is not given. So we have to find out V. VR is given, which is 150 volt. So R is given, VR is given. So when this current flows through this resistance R, so it makes a drop across it, which is VR. So VR is actually IR. So by using this, we can find out I, which is equal to VR by R. So it is 150 divided by 75. So I is equal to 2 ampere. This is one thing. Now we have to find out the supply voltage. So now we will find out, because we know that this V is equal to VR plus VL. So if we can find out VL, so it would be easy for, this is a phasor sum basically, right? This is phasor sum, right? So we can find out V easily. So there are two ways to find out V. Either we calculate VL or we calculate Z, because V is equal to I Z, right? So I has been calculated. So Z is equal to, now what is Z? Z is under root R square plus XL square. So XL is, what is XL? XL is 2 pi FL. So it is equal to 2 into pi into 50 into 318 into 10 raised to the power minus 3 ohms. So XL is equal to, so let us see what is the value of XL. So this is almost 100 ohm value XL. So Z will be equal to under root 75 square plus 100 square. So this is almost, let us see the value here. So this is equal to 15625, and by taking the square root it is 125 ohm. So V is equal to IZ, which is equal to 2 into 125, so 250 volt. So this is the answer for the supply voltage, and it is the RMS value. Now phase angle can be obtained by using the concept. We can use phi is equal to tan inverse XL by R. So we can use this particular formula to find out the value of phase angle. So the phase angle will be equal to, by putting the value of XL and then dividing it with R. So phase angle is 53.06 degree, and it is a lagging power factor. So it is lagging phase angle. So whenever your phase angle is positive, it is lagging generally, and if it is negative, it is a leading angle. So now we have calculated all the parameters, required parameters. We have calculated the voltage and we have calculated the phase angle here, right? So let us proceed further. Now here we have an RC circuit, series RC circuit, in which we have to find out the supply frequency and the phase angle between voltage and current, right? So the parameters which are given are 10 ohm resistance. So this is ohm. There are a lot of typo mistakes here. And then we have uh, current is this one. Uh, Capacitance is given. Supply voltage is given. All right. So let us find out the solution of this. Now, to find out the frequency, we can use the because we know that xc is equal to 1 upon 2 pi fc. So from here we can find out f, which is 1 upon now because f is not known, so we cannot find out xc also, right? So we need to apply some other concept to find out the frequency of the system. So it is 2 pi cxc. So that means to find out f, we need to find out this one, the capacitive reactance, right? So we know that Vc is the voltage across the capacitor, which is equal to I into Xc, right? So uh, from here, Xc is equal to Vc by I. So by using this equation, we can find out the value of capacitive reactance. And uh, so let us see what is the value. Now we know that the V is equal to VR plus Vc. It is the phasor sum, right? So V is equal to under root VR square plus Vc square, or Vc is equal to under root V square minus VR square, right? So V is 60 volts, which is given. So VR is IR, and this is equal to I is 5 ampere, which is given, into, and the resistance is 10 ohms, so it is equal to 50 volt. So VC is equal to under root 60 square minus 50 square. So it is 3600 minus 2500. So this is equal to, so VC is equal to, so let us see. So it is 33.17 volt. So VC has come. So we can find out XC by putting it here. So XC is equal to 33.17 divided by 5. So it is equal to 6.634 ohm. So now we have XC with us. So frequency is equal to 1 upon 2 into pi into 400 into 10 raised to the power minus 6. This is the value of capacitor, right? And into the capacitive reactance 6.634. So the values is, so this gives us 60 hertz. Similarly, the second point is phase angle. So phase angle can be obtained by using the formula tan inverse xc by r. So it is tan inverse xc is 6.634 and r is 10. So phi is equal to tan inverse 0.6634. So this is equal to 33.6 degree. Now because the circuit is a capacitive circuit, so we will write, because it is a leading phase angle. So phi is a leading phase angle in this case. So this is how we can solve the RC network and find out required parameters. Now let us come to the next question, in which there are two elements which are connected in series, which consume this much of power, and the power factor is this much leading. So when power factor is leading, that means it is an RC circuit, right? If the applied voltage is this much, find the circuit constants. So circuit constants are basically the value of R, the value of C, the value of XC, the value of Z. So these are the circuit constants which we have to find out. So the given things are, the power dissipated is 700 watt, and cos phi, which is the power factor, it is equal to 0.707 leading. So this means it is RC circuit. So let us draw this one. So you have resistance and capacitor. When connected to one another in series across an AC source, the value of this voltage is V, which is equal to 141.1 sine 314t plus 30 degrees. So this is the value of this voltage. So this is R, which is not given, and this is C, which is also not given. So let us try to find out. Now, the RMS value of voltage is equal to Vm by root 2, and this Vm is equal to 141.1 divided by root 2. So V is equal to, so it is basically 100 volt. So these parameters are interrelated to one another. We need to take care of that. So V has been calculated. C. How will we calculate the impedance? Impedance can be calculated by knowing the value of R and C. R can be calculated by knowing the value of current in this particular circuit. Xc can also be known by using the value of R and Z, sorry, by knowing the value of Vc, right? So now let us find out the value of I basically, because I is required to find out various other parameters, right? So the cos phi is equal to P by Vi. From here we have I is equal to P by V cos phi. So let us see. So I is equal to P is 700 watt divided by V is 100 and cos phi is 0.707. So this is 7 by 0.707. So the answer is 9.90 ampere. So this is the current that would flow in this particular circuit, right? So we also know that P is equal to I square R. So R is equal to P by I square. So it is 700 divided by 9.90 square. So R is equal to 700 divided by 98.029. So if we divide 700 by this one, we have 7.141 ohm. So this is the value of R. This is one circuit constant we have got. Now similarly, we can find out the value of XC also, right? To find out the value of XC, because XC is equal to 1 upon 2 pi FC. So F can be obtained by using this equation. So here if you see, uh, omega t is equal to 314t. So it is 2 pi. So t to t is cancelled. So 2 pi f is equal to 314. So now 2 pi f is equal to 314 here, right? So we can simply substitute this value here in this equation. So xc is equal to 1 upon 314c. Now because capacitance is also not given here, so we need to find out capacitance also. So to find out capacitance, we need Xc. To find out Xc, we need capacitance. So why can't we find out the value of Xc by using some other concept? So let us see how will we find out the value of Xc. Now we know that Z is equal to under root R square plus Xc square. So Xc is equal to under root Z square minus R square. So that means we need to find out Z, which is equal to V by I. So V is 100 and Z I is 9.9. So this is equal to 10. So this is almost equal to 10 ohm. All right. So this is almost equal to 10 ohm approximate value. Now we will put it here. We will see what is Xc. Xc is 10 square minus, now R is 7. So we will take it as 7 ohm approximately. So this can be assumed as 7 ohm. So this is 7 square and it is equal to under root 51. So under root 51 is 7.141 ohm. So Xc can also be assumed as 7 ohm approximately. right? Now by putting this value of Xc into this equation here, we can calculate the value of capacitor, which is equal to 450 microfarad. Now we have obtained all the required circuit constants. This is one circuit constant V, and then R is in circuit constant, C is circuit constant, Xc is circuit constant, right? And Z is one circuit constant, this one. So these are the four circuit constants that we have obtained in this particular question. Now let us come to the next question, which is given here. In this we have uh, an RC circuit basically. So this is an RC circuit which is connected to an AC source, and the current in this is 10 ampere, and the voltage is 200 volt, which is the RMS value, and the frequency is 50 hertz. We have to find out the resistance, capacitive reactance. R we have to find out, X, C we have to find out, and C we have to find out. So one thing which is given here is the leading the voltage current. How will you identify whether the given circuit is capacitive or inductive? It is by seeing whether leading or lagging is mentioned or not. So if leading is mentioned, that means it is a capacitive circuit, not an inductive circuit, right? As it is mentioned here, that the current of 10 ampere leading the voltage by 1/12 of the time period. Now, the time period T is of 2 pi radians or 360 degrees, right? So this is how you can calculate. Now, theta is basically 1/12 of this 360, right? So it is 30 degrees basically. So this is theta, right? So not theta, basically this is the phase angle, right? This is the phase angle. So either it can be taken as phi. We can write phi is equal to 30 degree, which is the phase angle, right? Now what we have to find out, we have to find out the resistance. So to find out resistance, let us find, how will we find out resistance? So resistance can be obtained by using the concept of this one, Z cos phi, because we know that cos phi is equal to R by Z, right? So Z is, we know, equal to V by I. So it is 200 divided by 10. So it is 20 ohm. So R is equal to 20 into cos 30 degree. So it is equal to uh, uh, 10 into root 3. So this is almost 17.32 ohm, right? So this is the value of resistance. Now, Xc can be obtained by using the formula, this one. We can use this particular formula. So it is Z square minus R square. So this is, let us see how much is the value. So it is 20 square minus 17.32 square. So this comes out to be 400 minus, so 17.32 square is 299. So almost 300, because 17.32 square is 299.9. So it is almost 300. So this is equal to 100 square root 100. So Xc is equal to 10 ohm. Now we can use this concept to find out the value of capacitor. So we have two parameters obtained here, right? So one parameter is the resistance. This is first thing that we have obtained. This is the second thing that we have obtained, and third is the capacitor. Capacitance, sorry. So capacitance is 1 by 314 into 10. So this is almost equal to 318 microfarad. So we have got all the three answers now. Now let us come to the next example. So it is already been solved here for the convenience and to save time also. So in this particular example, if you see, a 230 volt AC source is given, which is of 50 hertz frequency, and there is a, this is related to RLC circuit, right? So there is a coil basically which is of this much Henry, and then we have a resistance which is of 22.5 ohm basically, and we have a capacitor which is 6.8 microfarad, right? So we have to find out impedance of the circuit, current, phase, angle, and all that. So now, the impedance basically, because it is given by this particular formula, under root r square plus the difference of the two reactances and their square. So that means because r is already given, so we need to find out the value of xl and xc so that we can find out the value of z. So xl when calculated is equal to 18.85 ohm, and xc when calculated is equal to 468 ohm. So by substituting the values here, we have got z is equal to 449.2 ohm. Now, the current is obtained by using simple this equation, V is equal to I Z, right? So by using this equation, we have I is equal to V by Z, which is 0.512 ampere. And the phase angle can be obtained by simply using the equation, which is equal to tan inverse the imaginary part, which is XL minus XC divided by the real part, which is R. So by using this one, we have got minus. Now, when angle is negative, so that means it is leading one, right? Uh, when the resultant is on the upper quadrant, so this is positive, so it is lagging. For series AC circuits, this is for series AC circuits, right? And if it is here phi, it is negative, so it is leading basically, right? uh, so this is how we can relate it, right? It is also mentioned here that current is leading the voltage by some angle, right? Now the power factor can be obtained by simply R by Z. Either we can use R by Z or we can use cosine of phi basically. So power factor is 0.00557 leading, right? And the power consumed is VI cos phi, because we know that cos phi is equal to P by VI, where P is the power consumed. So P is equal to VI cosine of phi. So this is how we can find out. And the phasor diagram is shown here because it is more of a capacitive circuit, because the phase angle is leading here, the power factor is leading here. So power factor will lead only in the capacitive circuit. So the resultant is in the lower quadrant basically. The resultant is here, right? Let us come to the next example. This is also related to our LC circuit. In this, we have a coil which has a power factor of 0.8, and we have a coil which is connected with this capacitor, and this is the coil basically, right? This is the coil. Coil means which has R as well as L. Generally, we consider coil that only. The supply frequency is 50 hertz, and the potential difference across the coil is found to be equal to the potential difference across the capacitor. So that means the potential difference here and the potential difference here is same. Now we have to calculate the resistance and inductance value. So now uh, resistance R can be calculated by using see this particular formula which is given here. So cosine phi is already given, which is 0.8. We need to find out the impedance of the coil. So impedance of the coil will be, because we know that the potential drop across these two is same. So the impedance of this coil and impedance of this will be same, because the same current is flowing through these things. If I is same, V is same, then Z is also same. That is Z of coil, Z is impedance, is equal to Z of capacitor, right? So we need to calculate the Z, right? So because it is easy for us to calculate the capacitive reactance, so capacitive reactance is this much. So we know that the potential drop across the uh, coil is I into Z coil. So Z of coil is uh, sorry, V across coil is I into Z of the coil, right? And V across capacitor is I into XC. Now, because it is given in the statement that these two potential drops are same, so that means V of coil is equal to V of capacitor. So from here we have got Z coil and we have substituted the value here. We have got 23.2 ohm of the value of resistance, right? The second is we have to find out the inductance. So inductance can be obtained by using this formula. So for this formula, we need XL. So XL is obtained by using Z coil sine phi. This is also one way of finding the value. Otherwise, we can find out XL by using the concept because we know that uh, Z is equal to, for a series RLC circuit, Z is equal to R square plus XL minus XC square. But here, because the impedance across the combination of this is equal to this one, so it is not preferred to use this particular formula. So instead, what we can do is we can use the impedance triangle here, right? We can use impedance triangle here. So by using the impedance triangle, and this is phi, this is R, this is net reactance X. So we know that the perpendicular by hypotenuse, so X by Z is equal to sine of phi. So X is equal to Z sine phi, right? So we can use this one, right? So by using this, we have got this much value of the inductive reactance, and by substituting this value here in this particular formula, we have got the inductance, which is equal to 0.055 Henry. Now let us come to the parallel. Now let us come to the numerical related to a parallel AC circuit. So in this, we are given as a resistance of 20 ohm and a coil of 31.8 millihenry, and there is some negligible resistance are connected in parallel across this much source, right? So this is the circuit diagram for the given question. We have to find out the line current. So this is line current, basically the total current that is flowing in the circuitry. We have to find out the power factor and the power consumed by the circuit. Now, as we know that these components will have the same voltage drop across them. So that is the advantage here. So we can easily find out the current that flows through the resistance by using the formula V by R. So this is 11.5 ampere. And here, as we know, that the current IR is in phase with the voltage, right? This voltage. Now let us come to XL, means the inductor part. Because if we have to find out the current through the inductor, we need to use this particular formula here. And for that, we need XL. So XL is calculated by using formula 2 pi FL, because the frequency is given, L is given. So we can substitute the values here. So the answer for XL is 10 ohm. So we have substituted the value in this equation, and we have that the current is 23 ampere, and we know that in an inductor, current lags the voltage by 90 degrees, right? The second is we have to find out the power factor. So, uh, sorry, the line current, we have to find out the line current, right? And then we have to find out the power factor and power consumed. So the line current, basically this I, which is the line current, it is equal to the phasor sum of IR and IL. So that means I is equal to, the magnitude can be obtained by using this relation IR square plus IL square. So this is here. So we'll substitute the values of IR and IL. So we have got the line current, the total current basically, which is 25.71 ampere. Now we will find out the power factor, and the power factor, see, power factor can be obtained in various ways. We can obtain it from the voltage triangle, we can obtain it from the power triangle, we can obtain it from the impedance triangle, and we can also obtain this from the current triangle, right? So if you see here, this one, so this one, this is the base, this is the hypotenuse. So IR by I, right? This is cosine phi. So it is IR by I in this particular case. So it is 0.447 lagging. Now why we have used lagging? Because our circuit is inductive circuit. Okay. So the power consumed can be calculated by this formula. This is the general formula for the for calculating the power consumed by an AC circuit, and the value is 2643 watts, right? Now let us take another example of parallel AC circuit in which we have all the three components connected in parallel to one another. We have to find out the value of this current I and the power factor. So I is basically the phasor sum uh, of IR, IC, and IL, right? So IR is the current flowing through the resistance, IL is the current flowing through the inductor, and IC is the current flowing through the capacitor. So we need to find out the value of IR, IL, and IC. For that, we need the value of R, which is already given. So this is 10 ohm, right? Uh, we need to find out XL. So XL can be calculated by using this formula, which is 5 ohm. We need to find out XC. So XC is the capacitive reactance, which can be obtained by using this formula, and this is equal to 20 ohm. So V is given, and we know that all of them, because are in parallel, so they are sharing the same voltage. So 200 volt, 200 volt, and 200 volt, right? Uh, right? So IR is equal to V by R, so it is 20 ampere. IL is V by XL, so XL is 5 ohm, so it is 40 ampere. IC is 200 by 20, then it is 10 ampere. That means the current that flows through resistance is 20 ampere. Current that is flowing through inductor is 40 ampere, and the current that is flowing through capacitor is 10 ampere. Now we know that the phase difference between the current and the voltage in case of a resistance is 0. Phi is 0 degree. In case of inductor, voltage leads the current by 90 degree, right? And in case of a capacitor, current leads the voltage by 90 degree. This is the phasor representation. Now, second thing that we have to find out is the power factor. Sorry, first of all, we will find out the supply current. This, that means the line current, because it is the phasor sum of these three. So I is basically equal to IR plus JIL minus IC. So the magnitude is this one. By substituting the values here, we have got 36 ampere. Now the power factor of the circuit is cosine phi, which is equal to, as we discussed here in this also, it is IR by, means cosine phi is also equal to the real part. So let us write it here. So cos phi is can also be, the general representation is the real part divided by the total. So we can relate it like cos phi is equal to P by VI. So P is the real part of the power triangle, VI is the total power. Cos phi is equal to R by Z. So R is the real part of this impedance triangle, and Z is the total value, total quantity. So similarly, cos phi is equal to IR by I. So IR is the real part of the current, and I is the total current. So this is equal to 0.56 lagging. So the current here is, the net current is lagging the net voltage by 56. Means the power factor is lagging power factor in this case, right? Now let us come to the next part. Now let us come to the resonance, the numericals related to resonance in AC circuits. In these types of numerical, generally we are required to find out the resonant frequency and all other parameters at resonance. Like in the question number, this one, 14, the example 14, we have a resistance of 100 ohm basically, and then we have an inductance of this much micro Henry and a capacitor of 100 picofarad. The circuit is connected to 10 volt, so a variable frequency source. So we have resistance, we have an inductor, we have a capacitor. They are connected in series with one another, and we have a voltage source, AC voltage source, which is 10 volt, and it has certain frequency f, right, which is not given here. Now we have to calculate the resonant frequency, current at resonance, voltage, and across the capacitor and inductor and capacitor at resonance, right? So the resonant frequency is calculated by using the simple formula 1 by 2 pi under root LC. Now, because your inductance is given, because capacitance is given, so it is quite easy for us to calculate the resonant frequency. So which comes out to be 1.59 into 10 raised to the power 6 hertz. Now the current at resonance. Now we know that the impedance at resonance, impedance is equal to under root R square plus XL minus XC ka square. So at resonance, XL is equal to XC. So Z is equal to under root R square plus, and this is 0 now. So Z is equal to R. So that means if we have to find out the current I, the voltage is V. So V is equal to I into Z. So I is equal to V by Z, yani ki V by R. So the resonant current is V by R, which is 0.1 ampere. Now we have to find out the voltage across L and C at resonance. Now to calculate the voltage across this one, which is VL, let us say, and which is VC across capacitor, let us say, we need to find out, because we know that VL is nothing but it is IXL, and VC is nothing but it is IXC. So at resonance, VL is equal to IRXL and VC is equal to IRXC, right? So XL, XC we need to find out. Okay, so XL is obtained for the resonant frequency, which is given here, right? Similarly, uh, voltage across, because at resonance we know XL is equal to XC. So we can find out either of the two parameters. Either we can find out XL or we can find out XC. So at resonance, VL is equal to IR XL. So XL is 1000 ohms. So it is also equal to XC at resonance, right? So by putting the values here, we have got the answer. So now in the last question here, example number 15, we have a series RLC circuit with these parameters. R is 5 ohm and L and C are given and 200 volt source is given. We have to find out the resonant frequency. So resonant frequency is calculated by using this formula. So it is 50.33 hertz. So this is how we can solve the numerical related to the AC circuits. It is very easy to solve the numerical. We only have to remember the basic concept while solving the numericals related to series and parallel AC circuits, power factor and or resonance. And this is it for today's class. Thank you so much.